on in the 5G networks in terms of the physical layer and the error correction coding on the physical layer. Okay, so let us start. Unless you have some questions, maybe questions related to the homework, but you still have some more time to solve the homework assignment. But I think it was not too difficult, so probably most of you already solved it over Christmas. But anyway, if you have questions there, also feel free to ask me or write me an email, and we will see that we solve the questions. Okay, so let us start by looking at what we did last time, so before Christmas. We started talking about this low-density parity check codes, the LDPC codes. And they are usually described by providing their parity check matrix, which is typically a large matrix containing only few ones and many zeros, so so-called sparse matrix. Why does this? We'll understand today or maybe on Thursday. But first of all, we start by looking at parity check matrix. And we can also see that, of course, this parity check matrix also describes how the parity bits are calculated. Because where we have ones in the parity check matrix, here in the columns of H transpose or the rows of H, this means 1 times U0 plus 1 times U1 plus 1 times U2 plus 1 times P0 must be 0 in order for the code word to be a valid code word. So we know if the syndrome, this is what we get out here, is 0, so the 0 vector, we know it's a valid code word. So directly, this parity check matrix H describes how the parity bits can be calculated. So in our simple example here, we can derive this parity equations. Here I wrote it again, the parity equations, and how we can basically calculate the parity bits from our information bits if we just know this parity check matrix H. So in the low density parity check codes, often the generator matrices are not even provided. They are not interesting. Everything is done basically only by using this parity check matrix. So we can use it, multiply with the received sequence, check if the received sequence is a valid code word or not. Or we can also use the parity check matrix for the encoding procedure, as we have seen here. So you can imagine that this parity check equations will become a little bit more difficult if we don't have the identity matrix back here in the parity check matrix. We will actually see in the parity check matrices used in 5G, it's slightly different. For example, we would have another 1 here and a 1 here. But also then we will see that we can basically sequentially calculate the parity bits starting like from the lowest one, which then actually will also appear in the next parity check equation, but it's known from the step before. So we will also use parity check matrices in 5G systems, which are easy to implement the encoding routine. So this depends a bit on the structure, or this determines somehow the structure, how this parity check matrix will look like, or how a parity check matrix will look like if we want to use it also for efficient encoding. But we will get back to this later. Okay. So then we basically started with an example, considering just our well-known 7,4 Hamming code, treating this one as an LDPC code. Obviously, it will not be a very good LDPC code as this matrix is not sparse. So we have really many ones here and only a few zeros. So this will not be a really good matrix to decode it as an LDPC code. We talked about some properties of the codes, like the irregular or regular LDPC codes. So the irregular ones are really powerful, but mostly found like by trying random matrices and figuring out which one will perform best. So we will get to know some tricks and tweaks how we could improve a parity check matrix to get a better performance. So again, this will somehow be related to the structure of this parity check matrix, but we will understand this. And the regular LDPC codes, they can be efficiently encoded. So this has some advantages when it comes to the encoding process. Okay, then we approach the decoding. Of course, that's mostly interesting for this parity check code, for the low density parity check codes. The decoding being described in this kind of Tenor graph. So in the Tenor graph, we basically have a graphical illustration of the parity check matrix. So meaning, how are all the bits related to the parity checks? So if you go back one page to our parity check equations, you can see that, for example, here for our first syndrome bit or check bit, as we can also call it, what is important or what contributes to this one is the first information bit, the second information bit, the third information bit, and also the first parity bit going in here. And this is exactly what is illustrated in this kind of Tenor diagram. Back to this one. So our first parity bit, our first check bit or syndrome bit, what contributes to it is the first information bit, second information bit, third information bit, and the first parity bit. So this is just a graphical representation of the equations being described by the parity check matrix. Okay, and we made quite a simple model here in our example. We wanted to use a so-called binary symmetric erasure channel, where we basically have three possible channel outputs. So we move in zeros and ones, so our bits, map it to plus minus square root EC, or plus minus 1 in this case, for the transmission. And we do some decoding here, or detection. Our noisy received signal, we sample it, so not a very smart receiver, obviously, but it's just for the sake of simplicity here, just sample the points like in the middle of the bits and try to map back the sampled values to our information bits. So if the samples look more like a 0 bit or more like a 1 bit. And there we basically came up with this third output state that we basically model in this erasure type of model, where we say if we observe values like around 0, it could have been a 0 bit or it could have been a 1 bit. So we are not safe about the detection there. So let's just assign this so-called erasure symbol, where we are not sure what actually was transmitted. So a high probability that something goes wrong here. If we observe really large values, we are quite safe that a +1 was transmitted. So our bit was 0. If we observe very large negative values, we are quite safe that a -1 was transmitted corresponding to the 1 bit. But in the middle, in between, unsafe detection, we use the erasure symbol. And if we consider these three possibilities for received or detected values, and we just model a received sequence where we say, okay, a safe detected 1, some unsafe detection, so the value around 0, we are not sure about this one, some more safe ones, and 2 more unsure detected bits. And then let's see how we can then all the check bits need to be 0. this is basically how the parity check equations were defined. So we know at the end, the sum of all these guys here needs to be 0. We have a 1 bit coming from here, a 1 bit coming from here, a 0 bit coming from here. So this means in order for the sum of these 4 guys to be 0, this unsafe detected bit needs to be a 0. So basically, we can conclude on the value of this unsafe bit from the observations of the other bits. So this is also important for today, as things will become a little bit more difficult. We use a more difficult or more complicated channel model, but the principle is the same. So what information can we extract from the other bits on the bit that we are looking at? And in this case, we can basically conclude from the bits which are linked over this check node 1 to this bit node down here, that it is very likely that this bit must be a 0. So we feed forward information to the check nodes, we feed back information to the bit nodes, and we basically continue with this process. So in the first step, we could conclude here a 0 bit. We would forward again our information, and from this we could proceed with concluding here on the other missing or unsafe detected bits. So you can follow this example also on the lecture slides. We didn't do it really in such a detail, but it's easy to understand and to follow. Okay, so this is basically where we concluded last time. Finally, by looking at how things are done in practical systems, because this binary symmetric erasure channel is not really a channel model that is useful in our practical system. So what we should consider at least as an additive white Gaussian noise channel model, or even more difficult, more realistic channel models. But the AWGN channel is one that appears quite often, so it's good to have a look at this one and to understand what is going on in this case. So this means we need to think about how will this change if we consider like all possible real valued inputs. For our tenor diagram, we could use probabilities to feed back and forward, also called log likelihood ratios, what we will get to know today. So the determination of the values in this tenor diagram will be a bit more difficult. We will understand this. And yes, then we will also see actually how this decoding will work. Okay, and this is basically where we want to start today. So here we have a question. In case of generation of powerful irregular codes, computer search is done. What is this computer search all about? Okay. Of course, what you would do if you want to implement some computer search to find good parity check matrices is that you would basically come up with a bit error rate simulation where you basically take the parity check matrix as variable. So you try many different parity check matrices and see which one will result in the bit error, in the best bit error rate performance for a given channel model or for a given signal to noise ratio. Basically, you will just generate big parity check matrices, place randomly 1 entries there, and see which one works well. So this is basically how it could be done. And of course, we know some side constraints, what we will also get to know here. What should be avoided in this tenor graph. So I think the approach to go for it would be somehow a mixture of a random placement of entries in this parity check matrix, maybe followed by an additional stage to avoid structures in this parity check matrix, which obviously will yield in a performance degradation. For example, if just randomly 4 ones appear in a square. So we will see this will have a bad effect on the bit error rate performance. So this kind of structures should be avoided, but we will understand this later on. Okay, so let's see what we have to start with. So first of all, we need some more equations to describe basically what is being circled back and forth in this Tanner diagram. And therefore, we need to get to know the so-called log likelihood ratio, prerequisites. For the LDPC decoding. So typically, log likelihood ratios LLRs are used as for the decoding in the Tanner graph. So this means, therefore, we need to think about what this log likelihood ratios mean, how we can calculate them, and of course later on how they will be used in the Tanner diagram. So the LLR is a measure if a received value for example, y being y0, more likely resulted from a 1-bit which would be basically minus square root EC being transmitted, or from a 0-bit corresponding to a plus square root EC. And therefore, we will need to have a look at the distributions of these received values y. This one. So you know this also from Mike Wolf's lecture. So we have here the plus minus square root EC, so the transmitted values. We just need to be a little bit careful here. We are talking about energies at the receiver side, so be careful not to mix this up. But as we typically assume we have like a normalized channel, so no loss at the channel, the energy, the average energy per bit is the same at the transmitter as at the receiver. Of course, if we consider some loss during transmission, we would have to distinguish the transmit energy and the received energy. So what is important, of course, for our detection and decoding problem is the energy that is available at the receiver. Okay, we know here our distributions look like this. So, for example, this is the distribution of y, the received values given x, in the case y, given x being plus square root EC. So if we always transmit plus square root EC, this is the distribution that we will observe at the receiver. Of course, due to the noise, if we have large negative noise values, we will also receive or observe values being smaller than 0. And notice if we did a hard detection, this will be the cases where things go wrong. And of course, we have a second distribution, the conditional distribution if minus square root EC is transmitted. This will be Fy, distribution of the received values, given the transmitted values for the case the transmitted value was a minus square root EC. Okay, so you know this from Mike Wolf's lecture, the typical example for a binary modulation scheme where we transmit a plus minus square root EC, and this would be then the distributions that we observe at like the correlator output, so at our receiver. Now basically the question that we would like to answer is, so if we observe a certain value, y0, this would be the y-axis down here, or received values. Just assume square root EC being 1. So I observe a value, let's say, of 0.4. And now the question is, if I observe the value 0.4, what's the probability that a plus square root EC was transmitted? And what's the probability that a minus square root EC was transmitted? So this is basically the question that we would like to answer. And see, of course, we could calculate this. You know, in order to get probabilities from a probability density function, we need to solve an integral. So this would be the probability to observe a value around y0. I use here an interval width of epsilon. So this would describe the probability to observe a value within this interval epsilon around the value y0 if a plus square root EC was transmitted. And we can do the same basically for the case where minus square root EC was transmitted. And you see, of course, this is the smaller probability. So if we observe a value y0, it's more likely that a plus square root EC was transmitted as if a minus square root EC was transmitted. And we are interested in the ratio of these two probabilities. This is what we want to determine. Okay, so let's start by writing down this two conditional distributions. So fx given y, fy given x, this way around, fy given x from y given x being plus square root EC. There you see it's just this Gaussian distribution depending on the noise variance, of course. It's 1 over square root 2 pi sigma square. Sigma n, so the noise variance square times e to the power of minus y minus, now the mean value, square root EC square divided by 2 times the variance, 2 times sigma n square. So just the Gaussian distribution here with mean value being plus square root EC described by this equation, and the second guy fy given x of y given x being minus square root EC well, it's just the same with a different mean value. 1 over square root 2 pi sigma square times e to the power of minus y plus square root EC square divided by 2 sigma n square. It's written down here. From this, we could basically get our probabilities. So for example, the green one here, let's write it down like this. P of, so the probability to observe a value y that is larger than y0 minus epsilon half and smaller than y0 plus epsilon half. This will simply be the integral. So we just need to integrate over this interval epsilon. Our distribution here, f x given y of y given x being plus square root EC. So this will give me the probability to observe a value within this green interval if a value of plus square root EC was transmitted. And we basically just simplify this a bit. So for small values, or let's say as y is small, so this is maybe even better formulated, as epsilon is very small, approximation as rectangle So let me magnify this for you. So if we basically have here our Gaussian function and Here, that's the integral we want to solve. What we do, we simply approximate this by taking the function value like in the middle at y0 and using here just this rectangular shape. So you see, we will make a small mistake here, but as smaller, as more narrow epsilon will be, the smaller will be this error. So this means we use here is approximately equal to simply fy xf. Oh wait, it's fy given x. Here we have a mistake. Careful with this one here. We are always talking about the conditional distributions at the receiver, given we know a transmitted value. So also down here, we talk about fy given x of y given x is equal to plus square EC times epsilon. Okay, and you noticed one more typo here. Of course, the integral, we integrate over our variable epsilon, y. Yes. So basically, we want to think about this probability. We approximated it using this rectangular approximation. And now we can basically calculate both the probabilities, the green one and the red one, and set them in relationship. So this will be the next step, which actually defines this so-called log likelihood ratio. So the log likelihood ratio for y being y0. This is the natural logarithm between these two probabilities. So the probability to observe a value between y0 minus epsilon half and y0 plus, right in here, plus epsilon half under the condition that x being plus square root EC was transmitted. Divided by basically the same under the condition that x being minus square EC was transmitted. P of y minus epsilon half less or equal y0 here, y0 less than y0 plus epsilon half, given that x was a minus square EC. Actually, in the lecture slides, I used less or equal. But anyway, as we will let epsilon go to 0 later on, this doesn't really matter. And we now just put in what we already know. So it's the ln between these two distributions, f y given x of y given x being plus square root EC times epsilon, so this rectangular approximation to calculate the integral, divided by fy given x of y given x being minus square AC times epsilon. And now you already see what happens. Epsilon cancels out here. So we just get basically the ratio between these two probabilities. So here's the question, explain the log concept once more. Okay, yes, so it is maybe not so straightforward why we use the ln here of these probabilities. But we will see this right away as these distributions here are Gaussian distributed values, as we consider a Gaussian distributed noise model. Basically, the ln will simplify stuff. If we put input here now, or as we will right away input here these Gaussian distributions, taking the ln will basically simplify things a lot. So this is why typically this logarithmic ratio of these probabilities is used, because of the nature of this Gaussian distribution of the noise process. We will actually see that using the ln here basically also limits the range of values nicely. So in typical examples, you will have, for example, probabilities going really straight like towards 1, like to a safe detection. So 0.0999998 maybe, or 0.099997. And between these values can be better distinguished if we use a logarithmic scale there. So it's, yeah, simply a more suitable measure to describe the probabilities of our estimates. Okay.
Excuse me, sir.
Yes.
Can you show previous page for a second?
Yes.
Sir, I have a question.
Yes.
Yes.
Okay. So, sir, for decoding LDPC codes, we have our message pass algorithm, which we did earlier, and we have this log likelihood ratio. So these are two techniques for decoding LDPC code, isn't it?
Basically, the idea behind both is the same. So let me go back a bit further. You see, what we did here in this example can basically only be done if we use this channel model. If we have these 3 outputs from our channel or detector being either a 0, a 1, or an unsafe, this erasure symbol. If we would allow here basically the output of an additive white Gaussian noise channel, we would have here any real value, like the output can be 0.1, it can be 1.1, 1.2, minus 2.1, and so on. So somehow for this additive white Gaussian noise channel model, we have to deal with an arbitrary valued output here. And you see, this is why we need to consider something else to be forwarded between these nodes here. So for example, if we have more information here, like observations from the AWGN channel, we could work here, for example, with probabilities. I could calculate here the probability, for example, for this to be a 1. Let's look at this one. It's fairly close to the +1, what was transmitted. Probability for this to be a 1 could be like 90%. Probability for this to be a 0 could be like 10%. So we could also work here with probabilities instead of this decided values and forward probabilities to the node above. This is actually what we will also see later on. And then we could say, okay, if we know this is very likely to be a 1 coming from here, let's say 90% of 1, maybe here also 90% of 1, here 80% a 0. Then we know this sum of these values. So we could calculate the probability that this sum of values turns out to be a 1. And with this also the probability of this bit, for example, or the probability that a 1 at this position will make the parity bit or the check bit here to be a 0. So this is basically the next step when coming to a more advanced channel model, using here, instead of this 3 possible decided values, arbitrary values from our observations at the channel output, arbitrary values in the form of probabilities. So in the next logical step, basically not decided values would be passed back and forth here in the Tanner diagram, but probabilities. And these probabilities become even more handy if we use the log likelihood ratios instead of the probabilities. It's almost equivalent, just the range of values is more nice when looking at log likelihood ratios instead of probabilities. The math behind is pretty much the same, where we have joined probabilities for bits to appear. We have the product of probabilities, which will turn into a sum of log likelihood ratios. So it's not really a lot different if we exchange back and forth here probabilities or log likelihood ratios. But in practical systems, log likelihood ratios are used. Maybe it's also good to show you here this example with numbers. Let me see, I have it on the lecture slides. Just a second. We will get to this. But now it might help you understand this stuff. So here I have actually an example with values that were transmitted. So I assume I transmit here this bit, a valid code word from the 7,4 Hamming code. The bit values mapped to -1 or +1, or minus square root EC and plus square root EC. Then I model some noise, so adding some noise values, which results in this noisy observations. So it could be any real value here. And from this, we basically want to use the Tanner diagram to conclude on the other bits or to improve the probability of our estimates. So if we look at these received values, let's see where things could go wrong. So for example, here the last one, a 1 bit being mapped to -1. What we observe is a plus 0.2. So again, if we would just do a hard decision detection, we would say, okay, larger than 0, probably a +1 was transmitted, corresponding to a 0 bit. So here we would make actually a detection error if we just used hard decision detection. Here, so let's look at the first one. We basically receive a -0.8, so only a little noise influence here, noise being like +0.2, so little noise, received value almost the same as we transmitted. So this one is very likely to be a -1 that was transmitted or mapped a 1 bit. So here we have a high probability that this observation belongs to a bit value of 1, and also expressed now in terms of this log likelihood ratios. So if we observe a value -0.8, we can calculate the log likelihood ratio to be -5.8, so a fairly high value of the log likelihood ratio, meaning it's very likely that our observation is a 1 bit. We could express it in the same way in terms of probabilities. So if we observe a minus 0.8, the probability that the transmitted bit was a 1 is 99.7%. And of course, on the other side, we also have the probability of error. It could also be that I observe a minus 0.8 if a plus 1 was transmitted, with a noise amplitude being as large as like minus 1.8. So it's very unlikely that this large noise amplitude occurs. This means it's also very unlikely that we transmitted a 0. So basically, log likelihood ratio and probabilities are a measure on the reliability of our observation. So large log likelihood ratios, very high probability that what we observe is actually what we transmitted. Very low log likelihood ratio here, like this 1.4, means we are not really safe about our decision here. We observe a value which is somewhere like just in between the two possible values. See here with 80% probability, a 0 was transmitted. If we observe a plus 0.2, just with 19% probability, a minus 1 was transmitted. Here this would actually yield the detection error, but with cycling back and forth the probability in our tenor diagram, this will basically be corrected, as we can conclude from the other observations. Also, we can extract additional information on this bit here, which will have the consequence that when cycling back and forth information in this tenor diagram, the estimate on this here will improve. And finally, also the log likelihood ratio will turn out to be negative for this one here, and it will be decoded correctly.
So, sir, as the Euclidean distance between transmitted values and received value is going to decrease, our log likelihood ratio is going to increase. So that will give a better approximation that whether it has been decoded correct or wrong, isn't it?
Yes, that's basically the point that we would like to emphasize. So log likelihood ratio being a measure on how reliable our observation is when we compare it with the most likely transmitted bit. So if we observe a large negative value, it's very likely that a negative value was transmitted, which basically turns into a large negative log likelihood ratio. And the log likelihood ratio is basically used. It has another benefit. So just see how we would decode the message at the end. We would just use the signum function on the log likelihood ratio. Negative sign, -1, negative sign, -1, positive sign, +1. So also then the final step will be very easy using the signum function on our log likelihood values. Whereas with the probabilities, well, I kind of have to deal always with like two probabilities. The probability to be a 1 or the probability to be a 0. Whereas in the log likelihood ratio, we have a function of the ratio of the probabilities. So basically it's all concluded in one value. Okay, so let's see some more question. How the probabilities are calculated in this table. Yes, so the probabilities are just made up by a random number example. So of course I need to set the noise variance somehow. I said it like one slide before, noise variance like 0.5, which gives me random noise values here that I just add to my transmitted bits. So it's just an example with arbitrary numbers, which I wanted to use to give you a feeling for the meaning of this log likelihood ratios and how they are related to the probabilities of the big values. Okay, and one more question. Does this mean received values close to the intersection point of the normal curves are likely to be decoded falsely? Actually, it's not the see how to answer this in a good way. So the example where we would have a very low log likelihood ratio would be if you look at this one here. If you observe a sample being like right around 0, then the probability to be a 0 bit would be the same as the probability to be a 1 bit. So we would be 50% probability to be a 0 bit, 50% probability to be a 1 bit, if we are right in the middle. So we cannot really decide. For the log likelihood ratio, this will mean the ln of probability to be a 0, 1/2, divided by the probability to be a 1, 1/2, 1/2 by 1/2 is 1. The ln of 1 is 0. So the worst case, when we don't know at all what we do with our received value, the log likelihood ratio will turn out to be 0. That's the most unsafe case that can occur, being a value right in the middle between the decision values. If you look at the probability density functions, this would correspond to the case like observing a value here at 0, where the probabilities are equal. Yes, that's probably what you meant with the intersection point of the normal curves. Yes, exactly. At this point here, the probability would be the same that a +1 was transmitted as if a -1 was transmitted. The log likelihood ratio will be 0. So that's pretty useless, the most unsafe case that can occur. But also there, with feeding back and forth information in our tenor graph, we will basically be able to improve this estimate and at the end also come up with the correct value. But in the first stage, you are right, at the intersection of the curves, we have the most unsafe detection, the lowest log likelihood ratio. Okay, are there more questions so far? It's quite important to understand this well. Therefore, your question was really good now to get an idea on the feeling before we actually start calculate values. Okay. So let's see. So we stop there, where we have the ratio between these two guys. Actually, let's write this in brackets here. This is also the same. This reflects more the meaning as the ln between the probabilities to observe a value y0 if x being plus square root EC was transmitted. Divided by the probability to observe a y0 given x minus square root EC was transmitted. Now you will see why we use the ln here, because if I introduce now here these two distributions, 1 over square root 2 pi sigma square times e to the power of minus y minus square root EC square divided by 2 sigma n square, and dividing this by the second guy, 1 over square root 2 pi sigma n square times e to the power of minus y plus square root EC square divided by 2 sigma n square. You see the factor here will cancel out. We have the quotient between these two distributions, between these two exponential functions. So we can also write this as basically the product of the two functions. So let me rewrite this. ln e to the power of minus y minus square root EC square divided by 2 sigma n square multiply, just with the positive exponent here, e to the power of plus y plus square root EC square divided by 2 sigma n square. And now we can simply combine this. We have the product of exponential functions. This will turn into the sum of the exponents. Slowly. So this will be the ln of e to the power of minus y minus square EC divided by 2 sigma n square plus y plus square root EC squared divided by 2 sigma n square. And this just simplified further. So let's see. So we can take the ln already. So this will just give us a, so we could move the 1 over 2 sigma n squared to the front. What remains here will be minus, let's use an additional bracket not to mix up the signs here. This bracket squared, it's like a y square minus 2y square root EC plus EC plus, well, and here I don't need another bracket, we have a plus here. So we get a y square plus 2y square root EC plus EC just need to be a bit careful with the signs. We better write it once more. 1 over 2 sigma n square. We get a minus y square plus 2y square root EC minus EC plus y square plus 2y square root EC plus EC. Okay, so let's see what cancels out here. Minus this guy, minus plus this one, minus EC plus EC. So what remains here is, let's see. So what remains here is basically just the 1 over 2y squared EC plus 2y squared EC, so this is like 4. Something seems to be wrong here. 4y squared EC. It's okay, divided by 2 sigma n squared. Okay, so this is basically the probability or the ratio of the probabilities if we observe a value being y0 just a bit confused because I thought square root EC would cancel out. Let me just briefly think about this again. So actually there's a mistake on the lecture slide, so the EC will not cancel. Okay, so let's underline this. So actually here the factor of 2 cancels out. So, and we conclude for square root EC being 1, so normalized. We get the log likelihood ratio for observation y0 will be 2 times the observed value divided by sigma n squared. So this is basically how this log likelihood ratios in my example with the numbers have been calculated. So just the value of our observation, y0. So the larger the value is, the larger will be the log likelihood ratio. If we observe negative values, we will get a negative log likelihood ratios accordingly. The whole thing scaled by the noise variance. So for large noise variance, this log likelihood ratios will turn to be smaller, more unsafe detection. For very low noise variance, basically the log likelihood ratios will become large, meaning very safe detection. So just look at the quantities that influence this log likelihood ratios, and then it will be more clear. Maybe we use one example here from our slides that we get the numbers. So let's use this one here. So e.g. we use EC to be 1. Then I used, actually it was a bit more difficult. So let me see. We use a 7,4 Hamming code. This means code rate being 4/7, so 4 information bits, code word length 7. So this means our bit energy, EB, will be 7/4 times EC. So this is basically this effect on the reduced energy per coded bit. So it's like 1.75. So by applying this coding scheme, of course, we lose some energy for the coded bits. Energy 1 here means we would have, or we would need an energy per coded bit of 1.75. So, and I wanted to use signal to noise ratio. Defined in terms of EB over N0 in dB. So I wanted to use here 5 dB signal to noise ratio, like a typical value. I know EB, I know the logarithmic ratio here. So it means I also know the linear range, EB over N0. So not logarithmic will be 3.16. And from this, I can conclude on N0. So we have 0.55. I skip the units now. 0.55. And we know also from Mike Wolf's lecture, if this is the noise variance, we get the variance of the noise samples at the correlator output sigma n square to be N0 being like 0.28. So this is the noise variance that we need in order to model our process. And then let's come to some values from our table, just to make it not fully random. Okay. So transmitted bit value. Bit value. So we transmit a 1 bit mapped to plus minus square root EC, or in this case, plus minus 1. So we map the 1 bit to a -1 or minus square root EC. -1. Then we have a noise value. Actually, I also introduced the variables here. Let's call this here AI, XI, and this would be NI, so the corresponding noise sample. So let's assume we have this noise sample being 0.2. Which would give us a received value yi of -1 plus 0.2 will be -0.8. And now we basically have everything we need in order to calculate this log likelihood ratio. We have the noisy observation. and we have the noise variance. So this means we simply get the log likelihood ratio, LLR, of yi. So we call this L of yi. This turns out to be minus 5.8. So this means if we observe a minus 0.8, it's very likely that a minus 1 was transmitted. Maybe let's do one of the other examples. Maybe the last one, where we transmit also 1 bit being mapped to minus 1, but the noise is very large, so like a noise amplitude of 1.2, resulting in a received value of plus 0.2, we would get a log likelihood ratio of 1.4. Wrong detection. Well, but so far we did not do anything with the log likelihood ratio. So our decoding gain, our benefits from decoding will come in the sequel. This is just to get a feeling for this measure of log likelihood ratio that we use here later on in the Tanner diagram. Okay, so it's related to the value that we observe and to the noise variance. Okay, are there questions so far? So, okay, I also have an example here. Okay. So there's of course also the other way around. If I know a log likelihood ratio, I can also calculate the probabilities. Let's go back one slide. Here, so the log likelihood is the ln of the ratio of the probabilities. So I could also solve this for the probability to be that a plus square EC was transmitted and calculate this in terms of the log likelihood ratio. It's basically just turning the equations around, which is sometimes also needed and useful. So let's write here the other way around. From LLRs to probabilities. For example, I want to know if I observe an LLR of like minus 5.8, what's the probability that a minus 1 was transmitted? And somehow it should be like 99 point something %. So I want to close this link. So we know basically the L of y is the ln of the probabilities that for a certain observation y given x being +1 divided by the probability of y given x is -1. So this is basically just this ratio. And of course, we can simplify this. P of y given x being +1 divided by, well, the probability to be -1 is 1 minus the probability to be a +1. So we can basically use here this relationship. So I forgot here the equal sign. Try to keep the overview here. Write this more nicely. So it's P of y given x being +1 divided of P of y given x being +1. Let's also write this nicely. It's not a bracket, it's a straight dash here for the condition. Okay. So, and I want to solve this for this probability here. So here I have the relationship between the probability for the bit to be a +1 and the log likelihood ratio. Okay, so let's see how we do this. Just using the exponential function e to the power of L of y is equal to this ratio of the probabilities, P of y given x being +1 divided by 1 minus P of y given x being +1. Well, how can we solve this? Multiplying this guy to the other side, combining the expressions where we have the probability here. Let me see. So it will be e to the power of L of y times 1 minus P of y given x being +1 is equal to P of y given x being +1. Well, it's not so difficult now, it's straightforward. I multiply out and combine the probabilities. So it's e to the power of L of y minus e to the power of L of y times this probability as this probability bringing the probabilities together. So e to the power of L of y is P plus e to the power of L of y times P, factoring out the P, we are almost done, L of y. Yes, so what remains is a 1 plus the exponential, 1 plus e to the power of L of y times P, or P is equal to e to the power of L of y divided by 1 plus e to the power of L of y. So let's write this once more. This is P of y, so the probability that we get an observation with the value y if x being plus 1 was transmitted. And this is actually the same as saying the probability that x being plus 1 was transmitted. Let's combine this here that we can draw a box around it at the end. So P of x being plus 1 will be the e to the power of L of y divided by 1 plus e to the power of L of y and we could do the same for the probability for the bit to be a minus 1. So we would just replace the probability on top here with 1 minus the probability to be a minus 1, solving it in a similar way. We will get the second guy here, P of x being minus 1 will be, or we could do it even the other way around. If it's not a plus 1, it must be a minus 1. So it's 1 minus this quotient here. And if we simplify this, we would get e to the power of minus L of y divided by 1 plus e to the power of minus L of 1. Let's write underneath this here in the same way. For P of x being minus 1. And if we come back to our example, we would get the following numbers. From the example. If we have a L of yi being, so what did we get here? Minus 5.8. We get P of x being plus 1 to be 0.997. And we get P of x to be a minus 1 of like 0.003. So you see, we can use both of these quantities. We could describe the bits by using the probabilities or by using the log likelihood ratio. And we can calculate one out of the other. So here we have the question, 1 is mapped as minus 1. Yes, so basically this would be the probability P of AI to be 0, right? Yes, we map the 0 bit to +1, and this would be P of AI to be a 1 bit. So don't ask me why the mapping is done this way. Probably it would be more straightforward to map the 1 bit to the +1 and the 0 to the -1, but typically it's done the other way around. So the 1 bit is mapped to -1, the 0 bit is mapped to +1. Just be careful to distinguish here. But mostly we are talking now just about the plus and minus ones, keeping in mind that those are somehow the mapped values of our bits. So actually, if it comes to decoding performance, it doesn't really matter if you map it this way or the other way around. It's just like binary symbols. Okay, are there more questions related to this? So maybe let's go back again to our slide at the beginning. So look again at this here. So we tried to answer the question. So if we observe a certain value y0, then did this value result more likely from a +1 that was transmitted or from a -1 that was transmitted? And we figured out that, okay, if we observe larger values, it becomes more and more likely that a +1 was transmitted as if a -1 was transmitted. And the ratio between these two probabilities that we illustrated here is described by this log likelihood ratio. So if our log likelihood ratio is larger, meaning the green area, the green probability is a lot larger as the red probability here, then it's more likely that a +1 was transmitted. So log likelihood ratio being directly a measure which bit was most likely transmitted if we observe a certain value y. And at the end, we figured out that we can also calculate probabilities from our log likelihood ratio by coming back to this example here. And basically, this here is also a good page to motivate the usage of this LLR. If you look at the range of values here, these LLRs are fairly nice values, like between 0 and 10 or -10 and +10, whereas here you already start to get difficulties here with like the number range. For example, if we do a couple of iterations in our Tanner diagram, we will see that this LLRs will go to like 15, 20, and so on. So meaning really probabilities here, maybe like with 10 zeros and then a 1, where we have like numerical problems. We could face numerical problems here, which is not the case if we use this log likelihood ratio. So just from the range of numbers, also this log likelihood ratio are really handy to be used as measure. Okay, are there questions related to this one? Okay, so then this is basically where we want to continue next time and basically see, let's go back to our Tanner diagram, how instead of this decided values here, we can work with the probabilities and the log likelihood ratios in this Tanner diagram. So there we will have to answer one more kind of difficult question. We need to come up with probabilities here. For example, the probability that the sum of certain bit values here will turn out to be 0 or turn out to be 1. So this is one more theoretical thing that we need to derive. What's the probability that the sum of certain binary random values will turn out to be 1 or will turn out to be 0? But this can be also derived, and we will do this next time. But I think for today, we are fine, unless you have some questions.
Professor,
Yes.
I have one question. Like while solving the example in the notes, not with the table. Yeah, this one.
Yes.
Not here. The
Before.
previous one, yes. You modeled noise sample as 0.2. Like I didn't understood how you calculated this noise sample, or you have taken it.
This basically just comes from random value from a normal distributed process with zero mean and variance sigma n square. Like in our case, 0.28. So I just made this number example up from a short MATLAB program. So I generated this code word. There I know the bits. I mapped them to ±1, and I generated this noise sample by using the rand command, like generating random values in MATLAB with the correct noise variance. So those are random values which basically model the noise.
Okay.
Okay.
Thank you, Professor.
So we have one more. Go to the last page again. This one. Okay. Yes, this basically was just the other way around. If we can come from the probabilities to the log likelihood ratios, there must be also the other way around, how to come from the log likelihood ratio to the probabilities. So sometimes we might also need this one. If we know log likelihood ratios and we are interested in the probabilities, we can always calculate the probabilities if we know the log likelihood ratio. So just depending on what we are interested in. But we will see.
Sir, in the second last step on the left section of this page, probability of y by x is equal to +1 is equal to probability of x is equal to +1. So this, here only. So this +1 is the actual mapped value which we have done.
Yes.
Okay. Yeah.
So this would be like the plus square root EC that we transmitted. Or we call this also like xi, the transmitted value. Yes. Okay, some more questions. Okay, so then that's it for today. Thank you for your attention, and yes, we are looking forward to the next lecture to see you again on Thursday. All right, then take care and goodbye. Save this.